Today, we will talk about 8M5, Lesson 4, more examples of functions. And this is just, again, it's not maybe the best titled lesson that we do, but we'll get right to what the point of this lesson is. And it's really talking about nothing more than the concept of discrete functions versus non-discrete functions. And this is kind of a concept that's not this. I'm going to, on a scale of 1 to 10, I'm going to give this one about a 2 or a 3. Hopefully I can make it a 1 for you. Totally simple to understand. And most students will get this pretty quickly. The homework is pretty straightforward. It's identifying functions that are discrete or non-discrete. And by the way, we kind of have talked about discrete functions and non-discrete functions as examples all throughout linear equations, all through 8 and 4, without actually ever calling them out specifically which were which. So today we're going to focus on this very straightforward, or almost straightforward concept. But first, before we do that, let's review what a function is. It's a set of inputs that yield one output. So again, we can often look at it on a table like this and would say, call it like number of apples, and then the cost of apples. So we often look at our functions as a table. Remember, we look at them as tables, graphs, equations, and word problems. But we'd say like 0, 1, 2, 3, 4, and 0 apples would always cost at one store 0 cents. Where it say it's Safeway. And 1 apple would cost 40 cents. 2 apples would cost 80 cents. 3 apples would cost $1.20, and 4 apples would cost $1.60. And this is a function. This is our input, and this is our output. So one number will always give one output. One will never give you a different number at a certain store on a certain day. It'll always cost you the same amount. Okay, so this is an example of a number, giving you a number. Right? So the number 0 gives you the number 0. The number 1 gives you the number 40. The number 2 gives you the 80. The number 3 gives you 120 if you're dealing in cents. Now, you can also have other kinds of functions, and these hopefully aren't terribly confusing, but sometimes you can have your inputs be words. So let's look at an example of our inputs being words. Wow. Words. We'll take the word, and the input in this case will be a any word. And I'm going to see if you can guess the function, and then I'll tell it to you at the end. So the word could be apple. That's a word. But then a word could be, frisbee. And I'm going to say apple gives you the number, and then the output is the number. And you're gonna have to guess what this function does. Remember, you put something in, you get something out. This is an input. We put it into the input machine, some people call it, and this is our output. A frisbee would give you a 7. The word the would give you a 3. The word a would give you a 1. The word b would give you a 3. The word, how about the word Dave? That would give you a 4. Can anyone guess the function? If you can guess this function, raise your hand. All right, I'm calling on Susie. And Susie says the answer is it's the number of letters in the word. That's what our function does. It counts the number of letters in the word. Good. And so this will always give you, any given input will only give you exactly one output. right? The word Dave can't give you a 4 and a 5. It will only give you a 4 because there's only 4 letters. Every word has exactly one answer. And now notice, we can double up. These can be doubled. We can have duplicates. Outputs. We can have duplicate outputs. And this is still a function. Remember, this whole unit is about functions. So this is a function. Now, okay, so I just wanted to kind of remind you that we can have, functions don't have to just be numbers going to numbers. They can be words going to numbers. And then sometimes they can even be specific, like vegetables. So let's just do that one real quick. So I'll write 2 functions with vegetables. And on this side, it'll be, carrots. And over here, it's orange. And over here, it would be, let's see, celery, green. Green. So this is a function. This is a veg. And this is a color. Who likes vegetables? I love vegetables. Okay, and then here, this will be our input and our output, right? And now let's go to one more. You could have another function right next to that. This has our vegetable. And then it could have a number. And we could do the same thing as we did above. Carrot, like over here, our rule over here. So we could have a vegetable, carrot, and celery, where carrot gives you a 6 because that's the number of letters in carrot. And celery would also have 6. This would be, again, our input and our output. Okay. So again, we're talking about functions. Now, we're going to move on, and we're going to cover in a second here discrete and non-discrete functions. But I just wanted to remind you what functions are. Okay, moving forward. Now, and we're just going to jump right to the lesson summary. This is the lesson summary at the back of 8M5, lesson 4. And it says functions are classified as either discrete or non-discrete, not discrete. Discrete functions admit only individually separate input values. So let's write some examples. Whole numbers. Words in English language. Even, okay, and then some things that are not discrete are going to be like ranges. They're going to be things on an infinite range or on a continuum. So, like if you have all real numbers, like that would be like 0, 0.01 and 0. Well, it's basically, oops, sorry. Basically, this is like kind of like every number, and we'll get into this example. Fractional values. We're going to dig way deeper into this. Fractional values. So over here, whole numbers. You can think of this as you'd have 0, 1, 2, 3, but not what's in between. This would not include, say, 0.5 or 1.5 or 2.5. And over here, though, you could have 0 and 1 and 2, but it would also include 0.01, 0.02, like all, includes, what's between. We're going to dig deeper into this. Now, one key is you only look at the inputs. You only look at the inputs, the range of values for inputs are all that is, or all that, well, let's just say all that matters for discrete, for identifying whether it's discrete or not discrete functions. Okay. So let's go forward. I usually can hear all these words and I don't really get it until I get some examples. So let's move forward and see if these examples are going to help. Okay. Now, a function that assigns, so the one thing that we want to do here, let me go and let me do one more thing. Let's go ahead and give some examples here, and then we're going to come back. So these will be examples of functions of discrete. Remember, these are like whole. Discrete is like the input are whole numbers or unique, objects or people. And then not discrete is like, continuum of numbers on a range. Okay, so discrete functions are things like, number of cookies to their weight of cookies. Or the persons in the room to name. And these are your outputs, right? When I say to, this is your inputs, and this is your outputs. So the persons in the room to the name of person. So let's just look at these two examples real quick. So the name of the number of cookies to the weight of cookies would look like this. We'd say, well, 0 cookies have 0 weight, number of cookies to the weight. When one cookie, let's say one cookie weighs, 3 ounces. Two cookies weigh 6 ounces, and then 3 cookies. And let's say you can't have a part of a cookie. So this graph would look something like this. 0, 0, 1, 3, 2, 6, 3, 9. And there wouldn't be anything, all of the in-between, there's no in-betweens. And here, persons in room to name of person. So this would be like, the first person who entered the room would be maybe Dave. The second person who entered the room, number of person. Let's say we had these name tags with numbers on them. So the number of person to enter the room, 3 would be Susie. And 3 would be Fred. And 4 would be Juan. And 5 would be Anita. Okay, so these are discrete functions because there's no in between, right? There's no in between. Now let's think about a discrete function, and these will be things on a range. So this might be, an example might be, the distance I walked in given amount of time. So over here would be the time, say in minutes, and over here would be the distance in, say, yards. So in 0 minutes, I'd walk 0 yards. In 1 minute, let's say I walked, 200 yards. And in 2 minutes, I walked 400 yards. Well, this is still not discrete because I could say, well, in half a minute, I walked only 100 yards. And then in a quarter of a minute, I walked 50 yards. And then I could keep breaking them down over and over. And I could get down to, 3/4. I walked 150, but there's always something in between. So remember this graph over here I had for cookies and weight, I had these unique points or these discrete points for 0, 1, 2, and 3, and there's no in between. Over here, if I actually graphed this data, I would have something that looked like this. I would have a graph that has something for 0, for 1, but I'd have something for a half and a quarter and an eighth and a 16th. I'd have something for every little point. There would be no breaks. It would be infinite points. And that's really what it's about. It's like, it's an infinite for any given stretch of the function. Okay. Now, there are some cases you might say, well, Mr. Lipscomb, that's good. But here, this is actually an infinite number of points because I have 0, 1, 2, 3, 4. I could keep going on and on and on all the way to infinity for the number of cookies. All the way on and on. But this would still be discrete because you'd have breaks. You'd have breaks. You have discrete points on your line, and that's the whole key. You have the word discrete means unique or discrete means kind of identifiable. Identifiable points that stand alone. Just like the number of persons in this room. It's like the first person is Dave, the second person is Susie. There's no such thing as the 1.5 person. Just like our rule over here said we couldn't break our cookies in half, so there's no 0.5 and no 1.5 cookies. It's a whole number of cookies. On the other hand, over here, time can be broken down into infinite little slivers. Okay, so I think I've beaten a dead horse here. Let's move on to some examples, and let's see if we can really make this clear. And this is what your homework is going to involve. Now, remember, when we're identifying discrete or non-discrete, we only consider the inputs. We don't care about the outputs. So let's see if you can pause and identify which of these are discrete and not discrete. And if you do that, you're going to really be doing great. Okay, so now I assume you're back. So now let's look at this. So our input, let's just circle our inputs. Number of apples at the store, the time a person runs, an integer, a real number, and then each student in the class. So these are our inputs. This is all we care about. We don't worry about the outputs when we're just identifying discrete and not discrete. So let's see. Assigns a number of apples to the cost at a store. Well, you can't buy half an apple. You can't buy a part of Apple. So this is discrete. Right? So on your inputs, you'll have like a 0, 0, 1, 2, 3. Those are your inputs. So this is a discrete function, which is different than if, let's just say, for example, you bought, if you ever been to the store and you buy something in a bin, like flour out of a bin, not out of a bag, but they have these bins where you put in a little scooper and you pull things out. That'd be not discrete. But that's an aside. That's not one of our 6 problems here. The time a person runs. Whenever you talk about time, you're almost always talking about a continuum, right? Because they can run for a second, 2 seconds, 3 seconds, but they can, you can also map it. The input could be half a second, and you can break it to a quarter of a second. You run on a continuum. You don't just kind of appear somewhere after a second and after 2 seconds and after 3 seconds. It's a nice smooth curve. So this is not discrete. We actually kind of already talked about that example on the last slide. So that's not discrete. Now here, a function that assigns an integer to its first, don't even worry. On this one, I don't even worry about what the function does. I just say the input is an integer, right? So if the input's an integer, it's here, it's here, it's here, it's here, it's here, it's here. So this, if the input can only be an integer and no part of an integer, it has to be discrete. Okay. On the other hand, if the input is a real number, it's always not discrete. And so this one is also not discrete. I don't care that the output is always 24. That doesn't make it discrete or not discrete. We don't care about the output. The output doesn't matter. It's just the input being a real number makes it not discrete. Now, each student in class, whenever you talk about things, individual things, that's always discrete. Right? Because there's only 5 people in the class, 10 people in the class. Whenever the input is countable, with finite, well, let's just say whenever it's countable, it's discrete. Right? Because Joe, Fred, Susie, those are discrete people, easily countable. There's no in between. There's nothing in between Joe and Susie or in between Dave and Fred. Dave is, it's either Dave or Fred, nothing in between. Unlike real numbers, remember, real numbers, there's something in between 0 and 1, and that's a half. And then there's something in between 0 and a half, when that's a quarter. There's something in between a quarter and a half, and that's 3/8. There's something in between a half and 1, and that's 3/4. So as long as there's something in between every number, you're going to deal with non-discrete. You can break. It's a nice smooth curve. Now let's switch to another way. This is the verbal model way of looking at discrete and non-discrete numbers. Let's look at it from let's see, I think we're going to move in and look at it from a graphing point of view. So this might help. Some people are more graphical people. So let's look at things from the graphing point of view. And again, we're looking at inputs. So if I can take a slice here, if I take a slice, can I find, something in between my points? Yeah. Can I find something in between? Can I keep finding stuff in between, in between, in between? Then this thing is not discrete because it's smooth. It's a nice, smooth, non-breaking curve. Right? And you can probably just look at this and you can say discrete, 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 and which ones aren't discrete. But which one is discrete? This one has unique points. Right? So this one is discrete. Right? I can count my points. Now over here, this one stops at 2 spots. So the question is this discrete? This is the first time we've looked at this, discrete or not. Well, the test, remember the test. Can I count them? Can I count all the points? And the answer is no, I can't count all the points, because if I count this point here, there's one in between. And if I look at those 2 points, there's one between, in between, in between. So even though I have a range in my inputs only go from here to here, say -5 to 3 or whatever, I have an infinite number of points that are continuous. Right, so I can't count all my points. I can't give them names because I always have something in between any 2 points I count. I have a nice smooth continuous curve. So this is not discrete. I can't circle a point and say that one's by itself, or that one's by itself, or that one is by itself. I'm always circling more than one. So this one is not discrete. How about this one? Well, this one is discrete. I can circle my 3 points. So this one is discrete. You might want to try these last 4 on your own. You might want to pause and try while I just lay down, a happy cat. Why can't I lay that? Sometimes this happy cat doesn't really work out so well. But let's just put him on here. Happy cat, happy cat, happy cat, happy cat. All right, let's get back to these last few. So this one, in just like number 3, this one is not discrete because I have an infinite number. It's a nice smooth curve. Not discrete. This one is just 1 point by itself. Yep, discrete. I can circle it. Now this one is an infinite number of points, but only on the integers. So again, so this one is, I can circle individual points. So this one is discrete. Because I can identify discrete, unique points, this one is discrete. Even though these arrows show you that it goes on forever, I can still circle to my individual points. So this is kind of well, if it's infinite, it can still be discrete as long as each point can be identified with a nice clear circle that doesn't circle any other points. And then this last one is clearly not. I gave you an easy one at the end. This last one's clearly not discrete because it's a nice smooth curve. Okay, I hopefully, one last set of homework help. So which functions are discrete? So I'm going to give you, this is a verbal model. We're going back to verbal models. And in this one, we talk about the cost of gas as a function of gallons. So is that discrete or not discrete? We got to think about, can you buy fractions of gas, or do you have to buy it in discrete amounts? The same thing with the boxes of cereal. And then the last one is the persons in class versus their height. So we got to look at our inputs and see if we can identify unique inputs, or if this is going to be a or is this, sorry, is this going to be is this discrete or not discrete? Is it going to be a nice smooth function? Well, all right, pause and try. Pause and try, and then we'll do these as graphs and we'll do them as charts, and then we'll talk about them and see. Okay, hopefully you've done that. We're back now. Cost of gallon is function of gallons. So if you've ever gone to the gas station and seen your mom or dad fill up the car, or if you're old enough to drive, you can, you know that the gallons can be fractions. Right, so you can buy 0 for 0, you can buy 1 for $3, say, but you can also buy a half gallon for $1.50, or you can buy, 2/3 for $2. And so it's really, when you think about the cost of the gallons of gas, it's a smooth, continuous function. So it is not discrete, because you can always find numbers between any two other values, because it's a smooth, continuous. Your input number of gallons can be any fraction. The input can be any real number. Okay, the cost of a box of cereal, though, this one is clearly, you can't buy half a box of cereal. You can only buy 0, 1, 2, 3. And so the cost, say they're $5, 0 for 1, 5 for 2, sorry, 5 for 1, 0 for 0, $10 for 2, or 15 for 3. This is definitely discrete. And then each person in class, we've talked about this example. If Fred, he might be 5 feet tall. Susie might be 5 feet 2 inches tall. Mr. L, who I might be in class because I might be the teacher, I'm 6'4". I'm really tall. And so this is definitely discrete. So our question, let's Happy Cat. Why doesn't Happy Cat work all the time? This really is bothering me. Really bugging me. My Happy Cat doesn't come up all the time. All right, spinning Happy Cat. The whole key to the lesson, again, is basically, can you circle or identify each unique input, and is it not on a continuum? If it's a real number, typically real numbers or fractions as inputs would be non-discrete functions, and anything that's like integers, whole numbers, unique people, things that are identifiable. If you have, individual points on a graph, these are all examples of discrete functions. Okay, now hopefully that was a useful exercise, a useful lesson. It's, the concept of discrete versus non-discrete, it's really kind of an English, it's really semantic. It's not, I think it's just a way of creating awareness about the world, that there's when you lay mathematical models down that describe things like cost of gas, or the distance that you run, or the cost of a box of cereal, that those can be discrete functions or non-discrete functions, and you've got to consider the range, the potential input values when you're talking about each. When you're talking about buying gallons of gas, you're talking about any number, because you can buy any value or any amount of gasoline from 0 to as big as your tank is, and every little piece in between. Whereas if you're buying boxes of cereal, you got to buy 0, 1, 2, 3 discrete. Okay, hopefully I did a good job. If not, you know, I do better at some lessons and not so well at others, but I keep trying because that's the kind of person I am. So next we're going to do 8 in 5, lesson 5, and we're blazing through this 5th unit of Eureka Math 8th grade. Take care, and we'll see you next time.